welcome back. We are doing homework for Thermodynamics 1 course. This is homework number 5, which is first law analysis, energy balances, but for open systems versus closed systems. Okay. And so the first problem is basically you have air at 290 K and 80 kPa entering a diffuser of a jet. Okay. Can't remember which direction a diffuser is. Yeah, that sounds about right. So, something like this. Okay. Doesn't really matter. You have air coming in, you have air coming out. The math will figure itself out in terms of its shape. So it enters with a velocity of about 200 meters per second. The inlet area is 0.5. Area in is equal to 0.5 square meters. Okay. What is the temperature coming out? And that's all it has. But I might not need any more than that. Okay. Because, hey, maybe things will balance themselves out. They typically do. Okay. So, I got my system, I got my picture, I got my boundary, I got my assumptions. Okay. So I'm going to assume that this is steady state. Okay. I'm also going to assume that this happens so quickly that this is basically adiabatic. There's just not enough time for heat to transfer. I'm also going to assume that on a jet engine, now there is a jet engine, but the jet engine isn't part of this. This is just the diffuser part. And so there should be no work in this case. Okay. So I'm going to assume a steady state, it's adiabatic, no work, and I'm also going to assume that delta PE is approximately 0, but obviously not delta KE. I'm dropping to 100 meters per second. Okay, that's pretty big. That's the whole point of that's where the energy balance really comes from, is how much kinetic energy is being transferred to enthalpy. Okay. And so I might have some other assumptions, maybe like no leaks, but for the most part that's what I'm going to say. And so I have my mass balance, so ends n dot I minus summation of exits n dot E equals dN dt, my control volume. That goes to 0 because it's steady state. I only have one inlet, I only have one exit. And so what comes in is what comes out. Pretty straightforward. Okay. So I'm just going to call that n dot. Now again, do I know what that is? I don't know, but I'm going to do it anyways. Okay. Now I'm going to have my energy balance, which says ends n dot I hi plus 1/2 e squiggly squared I plus gzi minus exits of n dot E he plus 1/2 e squiggly squared E plus gze plus q dot plus work dot equals du plus ek plus ep d time of my control volume, but that all goes to 0 because it's steady state. The heat is pretty much 0 because it's adiabatic. The work is pretty much 0 because it's thing. There is no change in potential energy. And also we're going to assume that the velocity is negligible coming out. Okay, so VE is approximately 0. Okay. And so this simplifies down to n dot I hi plus 1/2 v squiggly squared I minus n dot E he equals 0. Oh, well, my moles are the same for both, okay, and because they're both multiplied by it, I can divide it out. So what I'm left with is hi minus he plus 1/2 v squiggly squared e equals 0. Okay. Well, I know this guy. I might know my enthalpy coming in, but really it's all about the difference. And so this is really my, my final equation. I could put, I could say that 1/2 v squiggly squared e is equal to he minus hi, or delta h, and then go from there. Okay. Now I need to decide, okay, what do I have? Do I have steam? Do I have an ideal gas? Or do I have a real system? Well, it says air. Well, last time I checked, air is pretty darn close to an ideal gas. And so this becomes Cp dt, okay, of air, okay, from T inlet to T exit, okay. Does it say anything else? No, it does not. So I do need to have the heat capacity, and so I go into the back of the book and I get my A, B, and D. So this is going to equal from T in to T exit of A plus B T plus D over T squared dt, because C and E are 0 for air. Do that integral, I have A Te minus T in plus B over 2, this is all times R, B over 2 times T exit squared minus T inlet squared, plus, or minus rather, minus D 1 over T exit minus 1 over T inlet, okay. Okay, all that's equal to 1/2 v squiggly squared n. Okay, I know my temperature coming in. I know my A, B, and C. The only thing I have left is TE. This is going to become a cubic though. So I can either use a cubic equation, cubic solver, or I can, plot this or use solver or something to figure out, okay, what is my exit temperature going to be? But I do technically have enough information to solve this. It's just going to be a kind of a beast to solve it by, definitely by, I can't solve it by hand unless you know how to solve cubics by hand, but I can use a computer program to solve this for me. So, but that's all there is to it.